All right, advent of code day 15. So, so you're going to get this grid, and it's going to be these are risk levels for stepping into any space. And you start at the top left space, and we're trying to go to the bottom right space. And um, to enter a space, you add that risk to your total risk score. And so we're looking for the lowest score to make it from top to bottom. So you can see that highlighted here. Um, One thing that's interesting is their thing is always moving down or right, but I don't think you can assume that. I think you could have puzzle input that has you going down, over, up, back. If you think of it as everything was nines except for ones, where you went there, then back, then up. It would definitely be the shortest path. That might not. We could probably try that shortcut and see if it just assuming we only move down and right. But that's the type of thing that I feel like when part two comes around, we'll just like really mess us up. So I'm probably not going to do that. Um, I've taken a few minutes here, and I read the problem before starting the video, and been looking into this algorithm that I remember from school, that I haven't dealt with in years, um, called Dijkstra's algorithm. And the basic idea is, I'm gonna pull it in here. It's set up like, you have this idea, and what you do is you start at the starting node. So in this case, it'll be like Reykjavik, and you look at, okay, what does it cost to get, you set the value for Reykjavik to 0, and then you say, okay, so going to London will cost me 4 and going to Oslo will cost me 5. um, and you put those both in like a temporary queue, and you don't those are not locked in yet, but you put them in a queue. And so then you take, okay, what's the shortest place I can go that I haven't locked in? Okay, well, in this case, it's London. So you go to London. London's now locked in at 4. So Reykjavik is 4, London is 0. And great. So what's the shortest place? So then, and then you add to the queue anything from London. So now we know Berlin is a total of 4, whatever London is, plus the new thing is 7. So we've locked in Reykjavik at 0. We've locked in London at 4. And then our queue is 5 to Oslo and 7 to Berlin. Well, the shortest one there is Oslo. So we lock in Oslo. The shortest way to go to Oslo is 5. I wonder if I should be doing this where I can draw. Um, well, I can do that real quick. Let's see. Open up a paint program here. So okay, so far we've locked in Reykjavik at 0. Oh no, that's terrible. I guess we'll try to type at 0. And we've locked in London at 4. And we know we have in our queue. And then we've locked in Oslo at 5. And so right now in our queue we have Berlin, visiting Berlin in 7, and we have visiting Berlin in 6, and we have visiting Moscow in 8. And so the shortest in there is visiting Berlin in 6. So we can put a 6 here for Berlin. And now this is where it's gonna get really hard without like seeing the queue, because now we add to the queue Rome in 8, we add to the queue Belgrade in 15, we add to, and I guess that's it. And so the shortest thing left is, let's see, 8, 15, and this is 8 as well. So we could do either of the 8s. So we'll do Rome in 8. We can lock that in. And then we can say, okay, we add to the queue Athens in 10. So we've got 15, we've got 8 here, so this will be 8. And now we add to the queue each of those steps. So what's left here is we can reach 15 there, we can go 13 there, we can go 10 there, so this will be the shortest one left. So Athens is now 10. And so what you basically are doing is you're locking in, and once you lock something in, you can know the value. I know the shortest way to Berlin is always going to be 6. And if I wanted to track the route, I would have to also track that it was through Oslo. So this is Dijkstra's. I don't know if that was a useful demonstration or not, but we're going to use a version of that to do this efficiently. I think that's my plan. So I haven't done it yet. So with that, let me grab I did not pre-save my input here. The VM15 example. And let me grab my puzzle input too. Puzzle input is big. Okay. All right, so let's give this algorithm a try. So what we're going to do is we're going to start with, oh, there's an interesting thing that's worth, well, I'll get it in a minute, I guess. So we don't need to read lines here. What do we want to do? We want to read this into a grid. So we will do, I guess we can do read lines. Let's see. So lines equals read lines dot, oops, dot read lines. That'll give us a bunch of lines, and then we just want to do G equals L line for line in lines. And for each of those, this is going to be L for L in line. We'll make it an int. That should give me a grid of integers. I probably need to strip this. See how that works. Python 3, day 15, 15 example, and I. So what do we have for G? Len G, len G0. All looks good. Okay, I got 10 by 10 grid. All right, so we're going to start at position. We're going to start at position 0. So we'll say Q equals, and so this, what we're going to do is we're going to store the Q as a risk score. So we know position 0 is 0, and the point row column value itself, like that. Okay. And so then we can say, let's see, there. Why did I have 2? That doesn't look right. Oh, so it's we need the 2. So the object, it's a single object here. It's a tuple that contains a score and then another tuple that is the point value or the location. So now we can do, so while Q, and this is what I wanted to, from, there's a library called heap Q. What's nice about, or heap Q, like that, import heap pop, heap push. What's nice about heap pop and heap push is it's going to allow me to say, give me the smallest item from a list. So I can say risk, comma, position equals heap pop Q. And that will spit out, in this case, there's only one value, but it'll find the lowest value. And when lowest value of tuples is sorted on the first value, so I'm going to get this from back, and I will it'll remove that from the list and return it to me, the smallest one, which is exactly what I want to do. And so then I'm going to say, let's see, come up here, let's say exit equals, yeah, exit equals len G, comma, len G 0. That's my row and my column. And that's, actually it's gonna be -1, I believe. Let's see, is that right? Yeah, it's gonna be -1. So if I reach, in this case, 9, 9, I'm done, I can stop. And so we say, if position equals exit, return, in this case, we're going to have we'll return the risk. I think we're done there. Now, if position is not exit, we're going to add all the neighbors. So we will do, let's do our, let's see. Up here, we need another neigh equals. I guess we're gonna do a get neighbors function just like we did in, I don't remember when, some previous one. Get nen neigh for r comma c, return r plus 1. We'll see if I can do this without screwing it up. This is the one I messed up that one time and it really cost me. R plus 1 of c, r minus 1 c, r comma c plus 1, and r comma c minus 1. Okay, that looks good. And so now we'll say, I'm going to go ahead and define, this is probably worth, so capital R equals, no, the maximum of rows is equal to len G, capital C for maximum of columns is len of G of 0. And that way I can just come down here and say, I'm gonna get rid of this exit. If position equals R minus 1, C minus 1, that's a little cleaner because I'll use R and C more. So now I'm going to say for R comma C in get, make this big, neigh of, just do star position. We've done that to expand that out. So I'm going to say, let's say if 0 is less than equal to R and R is less than R and 0 is less than or equal C. It's less than C. So basically, if I'm in a valid neighbor point, then I'm going to do heap push. See, what do I call this? Q. I'm going to heap push onto the queue, and the value I'm going to push is the risk score, which is going to be the current risk plus the risk of the new point. So G of R of C, and then the value that gets pushed on, or that's the score, and then the new, this in this case it's going to be R comma C. That looks good. So now I'm going to build out my heap. Now, the one issue I have here, I think, is my queue is going to get really big. So I need to check if, let's see, what do I need to check? I guess, because is this going to get infinitely big? No, I guess it's not. I mean, it's going to get big. It's going to be a lot of extra position, a lot of like, for every position, there could be like 7 or 8. The queue could grow to like 7 or 8 different ways to get to that same spot, which might just eat a lot of space in memory, but I think that's okay for now. I could try to figure out which ones I've like locked in as low, and then, whenever I pop, well, no, I guess that works. So when I pop something off the queue, it is locked in, if we remember from the algorithm. So let's add that to, if I pop it off the queue again, if I find another way to that one, it's by definition going to be worse, and I don't want it. So we will have locked equals like that. And in fact, let's make it set, because that'll make, we don't need to. And so then we can do, first of all, while I'm thinking of it, we need to indent this. There we go. So now, if we're in the endpoint, there we go. That's what's messed up. Okay, so now if we're in the finish point, we're done. We move on. Okay, if we're not at the finish point, we say if position locked. I guess we just continue. We do it. Go get the next one. Now we say locked.add position, and now we won't visit. Now once we get the shortest way to a position, we don't worry. We just remove it from the queue. If we get another path to that position, by definition, it's going to be longer. So we just continue. We just move on. And that looks pretty good. I don't know why I have return. Let's not break. And see, let's try this. Print part 1 risk. I got syntax error somewhere. Missing it. There we go. Pop, head pop. Where do I do that? Head. Part 140. What am I supposed to get here? 40. Oh, all right. Did that work? That's exciting. I'm not totally confident that was going to work. 508. All right. On to part 2. By the way, the entire cave is actually 5 times longer in both dimensions than you thought. The original is scanned. It's just one 5x5 tile that fills the full map. The original map repeats to the right and downwards, but the risk levels are 1 higher than the tile to the immediate left of it. Ah, okay. So the risk levels of 9 wrap around to 1. So if your original map had a position with risk level 8, the same position on each of the 25 tiles would be... Okay, so it goes 8, 9, 1, 2, 3, 9, 1, 2, 3. Okay. That shouldn't be... Okay. Each of the single so our full thing looks like this. So this 1 becomes a 2. 1, this becomes 1163 becomes 2274 becomes 3385 becomes 449. Yeah, okay. Okay, our same algorithm should work. So I think all we have to do is figure out how to make the new map, and we should be good. This is where I was already thinking ahead. Let's make this a function. So we do def find short path, and it's going to take in a G. Let's go like that. Now we're back to return risk. So this would be find short path G. Make sure that still works just before we... Okay. So now all we have to do is figure out how to define this new grid, and we will be good. So what if I say G2 is equal to for row in range len. Probably a better way to do this, but I'm just thinking this out here. G times 5 for column in range len G0 times 5 and what is the answer? So what's the best way to do this? So we want to loop over these distances. We need a G2 equals 0 times, let's do R2 equals this. C2 equals that. So this is going to be times the length of this is going to be C2 for R2. Does that look? That should make me? That should at least initialize me an array. I guess I don't even need that. I could just do just to make it an empty array. No, I can't do that. kind of regretting going with like a grid here and not a dictionary that takes a point, because then I would be basically done. If I guess I could go back and redo that. Maybe that's the better way to do it. Is there anything about that that's gonna get me in trouble? Well, let's see if I can fix this real quick. So I've got these two things. I'm going to define that G2 is now going to all be zeros. Then I just loop over it and I say G2 of row of column is equal to G of row mod R C of C, or C mod C. So this is going to map me back. So mod, it's, if I go 1 through 9, when I get to 10, mod 10, it's going to become 0 again. So that gets me back to the front. Then I just got to make the slight adjustment. So I got to do +1. No, not +1. Plus, let's see. Plus, so for every grid to the right I move, so that would be C divided by C. So that's, and double divisions is going to be integer, so it's going to round down. So if C is anything 0 through 9, that's just going to become 0. If C becomes 10, 11, 12, all the way through 19, that'll just be 1, etc. Now the other challenge I have is how do I handle the wrapper? So sorry, I also need to do R by R. So now I've managed incrementing it as far as I go. Guess I can do if G2 of R of C is greater than 9, G2 of R of C minus equals 9. So if it's bigger than 9, so it's 10, we wrap back to 1. And we're never going to get more than 1 wrap worth, right? We're never going to go above 19 or above 18, because we're only going up to 5 things. So let's see. Oh, we could have one in our 5, 0, 1, 2. We could have 4 plus 4. Yeah, so the most we're going to have is 8. So we'll always be within our, this should always handle it. So if that works, I'm a little skeptical if that's right or not, but if that grid is correct, then we can do part 2, find short path G2, like that, and it would just be done. Let's see, where's our example? Int objects not iterable. Oh, range len. Oh, I don't need len. Need range. I already have the integer. R not defined. These are all R2s. I think. Let's see. No, these are not all. I need to get C. I define those, but I put them in the function. So R equals len G. C equals len G0. 40 and 315. 315. All right, and that was fast too. I think I mentioned at the beginning, I was really tempted to try to do this with like some kind of recursion, and I think it would have just been a disaster. Okay. Ooh, that was still pretty fast. Let's see. All right. That was an incredibly difficult problem, and I'll be honest, I took a good 20 minutes of reading before I jumped on here to start recording, because I thought watching me read about Dijkstra's algorithm would not be a very interesting video. But still, I'm pretty surprised at how fast we got through that. We didn't make any really silly errors today, so that's nice. So yeah, let's go back and just review again what we did, just to see if we can lock it in. So for part 1, this is the really challenging part, and this is the part where I think there's a ton of rabbit holes I could have gone down, that, again, by spending that, if I was trying to do this competitively, sitting at midnight trying to be the first player, I probably would have just floundered a lot in this problem. But by stepping back and saying, okay, my gut instinct is to like do some sort of recursion where I, for each point, then call again on the next point. But the size of the grid, especially in part two, is going to make that really hard. The other thing, so spending time looking up Dijkstra's algorithm and seeing how it worked was certainly valuable for me. I don't know if my explanation at the beginning was super useful, but basically what we're going to do is we're going to start with a Q, which is our point, will be our starting point. And we're going to, again, if you think about this, we're going to then still, as long as there's a Q left, or really until we reach our endpoint, we will get the shortest value in the queue. So the thing that's the cheapest to visit. And we will then, if that's the endpoint, we're done because we found the shortest way to get there. If it's not the endpoint, but we've already been to that point, we've already found a cheaper way to that point, then we're just going to continue because we'll go get the next point. Okay, so now we're at the way we've gotten to a point and it's the cheapest way to get there. So now we've locked in that point. We know the cheapest way to get to that point. So we'll add that position to there. Again, if we cared about going to any point other than the last one, we would also lock in, we wouldn't just add the position, but we'd add the cost to get there as well, because it would be nice to know. But we don't care about it for this problem. So then, now that we found the cheapest way to get to that position, we can add to the queue all of its neighbors. And the cost, is if I go from this point to each neighbor, how much is it going to cost? So I then loop over, and as long as it's in the grid, I add that to the queue, and then I go get the next thing from the queue. And now, so what's cool about this is, I'm always going to the next shortest way, path. And that means that there's going to be lots of things get added to the queue as potential paths, but I'm always going to, when I get to a point, it is going to be this, by definition, the shortest way to get there. So this is cool and it's relatively fast. Probably didn't explain it great. Go read about Dijkstra's algorithm. Should spell that. It's a weird D. It starts with DJ. Yeah, there you go. So go read about Dijkstra's algorithm if you want more details on that. But anyway, so that solved us when we got to we got part one. For part two, the only challenge then, because of the good work we did setting up part one and doing it in a very efficient time efficient way, all we had to do was basically create this modified grid, and we did that by, I could have used like a default dict or something, but I just created a grid that was full of zeros, and then I went through and added the new values, and so this was the only tricky part here, was coming up with the idea that for each for each time that the row or column was greater than 9, I needed to add 1, and then if the total was greater than 9, I needed to do that loop back. And I couldn't just do that with a mod because I needed to subtract 9, not 10, because it goes 1 through 9 and then it goes back to 1, so 0 is never involved. So I made that a little bit weird, but not too big a deal. Awesome. Thank you so much for sticking around to the end. It was hope this was interesting and you learned something today, and I will talk to you next time.